So in this video, we are finally ready to actually start solving differential equations. And we're going to start off by taking a look at a first order differential equation. Recall that in the previous video we talked about classifying differential equations, and we can see that this is a first order because it only contains the first derivative, and it is a linear equation because we are taking a and b to be constants. So this is probably the most simple form of a first order linear differential equation, where a and b are both constants. So let's get right to it. I'm going to rewrite y prime as dy dx, and this is going to be equal to ay plus b. So the first thing that I want to do is I want to get rid of this coefficient on the y. Now you don't have to do that first, but I'm going to do that because it's going to make integrating this a little easier. So let's just divide both sides of this equation by a. So what I get is 1 over a dy dx is equal to y plus b over a. And now what I want to do is I want to get the dy's with the y's and put the dx on the other side so that I can integrate. So I'm going to divide by this entire term on both sides, and then I'm going to multiply over the dx to get it on the right side. So when I do this rearrangement, I get dy over y plus b over a, and this is equal to a dx. So now we can actually integrate this because all of the y's are with the dy, and then I have the dx on the opposite side. So I can integrate both sides. And recall from calculus that the integral of this expression is just the natural log of y plus b over a. And this is going to equal ax because the integral of a dx is just ax. And then I'm also going to add a constant of integration. And the reason why I need that constant of integration is because this is an indefinite integral. I'm not evaluating it at two limits. So I need this plus c right here. So now what I'm going to do is take the exponential of both sides. So e to all of that and e to all of this. And the e and the ln cancel out, leaving just y plus b over a is equal to e to the ax plus c, where I can simplify this expression to c1 e to the ax. Basically all that I did was recognize that this expression is actually e to the ax times e to the c, and e to the c is a constant, so I just define it as a new constant in front of this e to the ax now. But you guys should already know that from calculus. So anyway, now I can solve for y, and what I get is y is equal to c1 e to the ax minus b over a. So this is the form of the general solution to this equation. And notice that all we had to do was separate the differential equations to split up the y's and x's and then integrate. So since c1 is an arbitrary constant, what we need to accompany this differential equation is what's called an initial condition. So I need something like y of 0 is equal to y naught. So we can apply this initial condition by enforcing it through this equation. So I can say, all right, y of 0 is equal to c1 e to the a times 0 minus b over a, which simplifies to c1 minus b over a, because e to the 0 is 1. But from this initial condition, I know that this has to equal y naught. So now I can use this equation and solve for c1. So c1 is equal to y naught plus b over a. So if I rewrite this equation by plugging in for c1, I get y is equal to y naught plus b over a times e to the ax minus b over a. So this would be the form of our unique solution given the initial condition y of 0 is equal to y naught. So if we had a differential equation of the form that we started with, which was y prime is equal to ay plus b, if we had a differential equation of this form where a and b were constants, and we also had an initial condition such that y of 0 is equal to y naught, then we can just come back to our solution here and just plug in the corresponding values of a, b, and y naught. And we can take that as our solution. So in the next video, we're going to consider a physics problem that has a differential equation of this form right here, and we're going to integrate and get a solution, and then we're going to compare it with this result that I have boxed in purple. So thanks for watching, and I will see you guys in the next video.